Today we are going to talk about electric potential energy. We have seen, let me just remind you what we've seen. We've seen the electric force that exists between two charges. We've seen K, Q1, Q2 over R12 squared, right? And of course, this is a vector, so we usually include an r hat in there, which is the unit vector pointing from Q1 to Q2, the distance between the two charges, basically. This is the vector that points along that direction. Very often we write this in terms of its magnitude, so we leave off the vector notation here and the r hat here. But just to be complete, we're going to do this. And let me remind you of the procedure we went through after this. We figured out that, okay, that's great. There's a force between two charges. What I want to do now is to characterize the influence of one charge on the space around it. And to do that, I didn't invent, but I defined a new concept called the electric field. And I defined it like this: KQ over r squared. And to be complete, we'll put in the vector notation. Q is now just one charge. Notice there's no subscript because I don't need a subscript. I don't have any charges to differentiate. So I've got just a Q. And R now is not the distance between two charges. R is the distance between this charge and my observation point, wherever I'm choosing to evaluate the electric field. Want to know what the electric field is 10 meters away? You plug in 10 meters here. All right, now, of course, the electric field is a vector, so I put the vector nature on there. R hat now is a unit vector that points along the line connecting Q and my observation point, wherever I'm checking to find out what the E field is. All right, so this is all stuff that we know. Now, we're gonna talk today about potential energy between two charges. And I put this up here to remind you because we're going to go through a pretty similar process. But first, let me say that I hope that it's obvious that there is potential energy between these two charges. Let me just do a really sort of grassroots investigation of potential energy, right? Let's say I have here a man holding a ball. What happens if he lets that ball go? The ball falls down, right? It falls down and it hits the ground. Now, without getting too caught up into, well, where's your 0 point and how much potential energy does it have, it's got to be obvious that this ball has gravitational potential energy, because if I let it go, that potential energy starts to turn into kinetic energy. It falls down, right? That's a fantastic way to tell if something has potential energy. And if I set the ball on the ground, of course, it could have potential energy with reference to some other reference point, right? But just common sense here. We're doing a really crude explanation here. If I drop it, it falls. It's got to have potential energy. I hope that makes some sense, because the kinetic energy that it develops has to come from somewhere. All right, do the same sort of thing here. Take a positive charge and put it next to another positive charge and hold them in place. Now, let one of them go. Assuming it's free to move, what is it going to do? It's going to accelerate that way, right? It's going to accelerate because there's a force. But as I hope we saw in Physics 1, a force and acceleration is only one way to characterize a physical system. The other way is, another way is with energy. And so what I can say now, just like the ball falls, and that tells me it's got some sort of gravitational potential energy, this charge moves away, which tells me that this system has some sort of potential energy. It's not gravitational. It is, in fact, electrical potential energy. Just like potential energy exists between the mass of the ball and the mass of the earth, which is attracting it, potential energy exists between this charge and this charge, which is being repelled by it. If I made this a negative charge, right, if I put a negative Q here and I let it go, it's also going to move. It's going to move toward the positive charge. But the fact that it's going to do that tells me that there's got to be some sort of electrical potential energy. I can also figure out that I'm going to have to worry, or at least I'm going to have to be cautious about signs here, because electricity is attractive and repulsive. Gravity is always attractive. So while I didn't have to worry too much about the sign of potential energy here, I mean, maybe a little bit, here I'm going to have to be really careful with it. That can lead to some confusion, but we'll talk about it when we get there. Okay, how do I characterize this potential energy? I'm just going to skip to the punchline. The potential energy, which we usually write as a U in this class, and I'm going to subscript this with a C for Coulomb, just like I subscript the force with a C for Coulomb, the Coulomb force. The electrical potential energy between two charges is given by this expression, K Q1 Q2 over R1 2. And I'm done. So, good news, this is really similar. Bad news, it's not quite the same thing. We got to remember a couple of things. First of all, please notice this is not a vector. Energy is never a vector, right? This doesn't mean it's not directional. Energy moves around, so that implies a direction, but it's not a direction in space, right? It's a direction into a system or out of a system. It's not a direction like X, Y. It's a direction given by work, right? If we do work on a system, that's energy moving into a system. Work done by the system is energy leaving the system. So it is directional, but it's not directional in a spatial dimension. So it's not a vector, definitely not. So I don't have an R hat, I don't have a vector symbol. Also notice the denominator here is to the first power, not squared. This is still the distance between the centers of these two charges, but it now appears as just R, not R squared. So this is the potential energy that exists between 2 point charges. And I can ask questions like, what is the potential energy between, this charge and this charge? If this is Q and this is maybe some 2Q. We've done similar problems. I asked, what's the force on this charge due to this charge? Or maybe I could ask, what's the force on this charge due to this charge? And you know how to do that, right? You draw a free body diagram of that, figure out the direction of the force. You add it up using this formula here, not this one, but this one. We do the same thing here. What is the potential energy arising between these two charges? Well, U here in this case is going to be K, my Coulomb constant. Q1, Q2, in this case it's Q and 2Q over, I guess I need a distance, let's call this distance D over D. Not squared, just D, right? So I get K 2Q squared over D. Plain and simple. This is really not that bad. I hope we see that just as in Physics 1, if you understand how the energy works, solving problems using energy is actually a lot easier than solving problems using forces. This is pretty cut and dried. Okay, so this is the potential energy between two charges. Of course, if I have another charge here, I'm going to have another term, and we'll see examples like that. You'll have more terms as you bring in more charges, but we'll see examples of that in a little bit. First of all, I want to follow this on through using similar processes to how we got to the electric field. So let me get a new sheet of paper and run through the same line of thinking. Right? Potential energy, let me make sure I'm in frame there. Gotta move over a little bit. That'll work. Okay, potential energy exists between two charges. So just like I thought it was silly to only be able to characterize a system mathematically if there are two charges with forces, right? It's silly that I can't talk about the influence of one charge on the space around it. I think it's silly to only be able to talk about anything with this system if I have two charges. I'm going to do the exact same thing I did with my forces. How did I turn a force into a field? I divided out one of the charges and I got rid of my subscript. I redefined my subscript. So let me do the same thing here. potential energy. Now I'm going to divide through by, let's say, Q2, and I'm going to leave Q1. So I'm going to get rid of the subscripts here. This is something we've seen before, so I'm hoping this is okay. And that's what I get, right? Now, keep in mind, these are different Qs, right? This is, maybe I'll say Q prime here, because I divided out one of these charges, but not the other. But what I'm going to do with this term is I'm going to redefine it as this new quantity, which I will call the electric potential, right? V is electric potential. It is an unfortunate name. It really is. Because what is U? This is the electric potential energy. And it's really unfortunate that these names are so similar because that makes them confusing. Force and field are not that similar, so that's not that confusing. These are really similar, which makes it really confusing. But notice what the electric potential notice what the electrical potential is. It's the potential energy per unit charge. Just like the field is the force per unit charge, this is the potential energy per unit charge. So I'm not going to write this middle term anymore. I'm just going to write the V for potential, which is what I will say. I will hardly ever say electric potential. I'm going to say potential, and it's just going to be understood that I mean the electric potential. I will do my best to say potential energy when I mean potential energy, and potential when I mean energy per unit charge. Okay, that's equal now to KQ over R, where now Q is my source charge. It's the charge from which this potential arises, and R is the distance between that source charge and my point of observation. Where am I evaluating the potential, right? Just like where am I evaluating the field, that R told me that distance. Now this R tells me the distance between this charge, which is producing the potential, and the point of observation. All right, units of potential. Well, if I wanted to, I could go look up the units of K and get the units of Q, which are coulombs, and R, which is meters, and put them all together. But let me save you the time. After I do that, I'm going to recognize that it's a ridiculous amount of things, and I'm going to also remember that I'm an inherently lazy physicist, and I don't like writing all these letters that I have to, so I'm going to wrap all those things up and name it after somebody famous, which is what I always do to units that are obnoxious, right? We did the same thing with newtons. I'm going to name it after a man named Alexander Volta. I'm going to call this a volt. Units of this are volts. Or you can, instead of calling it the potential, some people will refer to it as the voltage, although that's a little misleading. This is only the potential in specific cases. But for this class, we can probably get away with, if you say voltage, I'll know that you mean potential. If I say voltage, you know that I'll mean the electric potential. But the units are volts, which is something that we've all heard of, right, before. The outlets in your wall are 110 volts. If you have a smartphone, chances are its charger is 5 volt. We've all dealt with 9 volt batteries. AAAs are 1.5 volts, things like that. Lantern batteries are 12 volts, and it goes on and on. We know a little bit about what volts are. At least we've used them in everyday life. But this is the electric potential, or the voltage, although I would much prefer the term potential, of a point charge. This is the general expression of that. Of course, to get back to potential energy, if this is the potential energy per unit charge, right, that means Q times the voltage is equal to the potential energy. That is to say, if you're given some voltage and you insert a charge Q, that charge, then has potential energy given by this expression QV. Better way to say it is there is potential energy exists between this charge and the whatever charges are producing this voltage. Okay, so of course it's the video. You can pause and digest if you need to, but I want to on this page give you kind of a summary of what we just did. We figured out that the Coulomb force, I'm just dealing with magnitudes, is K Q1 Q2 over R12 squared. And then from there I define the electric field as KQ over R. Of course, these two led me to a shortcut, right? If I'm given two charges and I want to know the force between them, this is my guy. If I'm given one charge and I want to know the field, this is my guy. If I'm given a field without caring what the source charges are and I put a charge in that field, this is my guy to give me the force, right? All these things are related. It's just what I'm given determines which one I use. Given two charges, got to use this one. Given a field and a charge inside it, use this one. All right, now, new stuff. Potential energy between two charges, KQ1, Q2 over R12. From there, talk about the potential of one charge, KQ over R. Oh, squared up there, my fault. Yeah, this is definitely squared, just like it's squared here. All right. Potential energy between two charges. This is my guy. Potential arising from one charge. This is my guy. Give me a potential, put a charge in it. How much potential energy does it have? This is my guy. So hopefully you see the similarities here. And I need more paper, which means I need to open a bag of paper. Give me a second. I'm going to talk while I do this. Hopefully, you see the similarities between these expressions and the similarities in how we use them. The upshot is, potential energy is easier to use because it's not a vector, right? We like that. It is not a vector. Okay, so one thing of which I want to make you aware, one of the pitfalls that's going to come in because we have signs now on our charges. So when we talked about the electric field, in some ways we interfered with nature a little bit. And so let me write this down. We chose how to draw field lines, right? Remember, we said field lines are going to go from positive to negative charges. Does nature do this? No. Nature does not care which direction you put on a field line. Like, nature doesn't even really care about our field lines. Nature cares about the field, and that's enough for nature. But when we need to characterize it, we do this. And we had to make a decision. So what we did was that we defined field lines pointing from positive to negative. In effect, we imposed our will on top of nature, although it doesn't affect nature, it just affects how we characterize nature. We're going to see that continue here. So what we're going to say is that now, my next rule for field lines, now that I understand this, is that field lines point in the direction of decreasing potential. Right? Decreasing potential. Now, be careful here because potential is the direction. Well, so the only thing that's physically meaningful about potential energy is how it changes. The only thing that's different, that's physically meaningful about electric potential, is how it changes between one point and another. When I was dealing with gravitational potential energy, I am still free and was free to define my 0 point wherever I want to, which led to characterizing the same system as having positive potential energy or negative potential energy just by moving your 0 point. For instance, if you have a pen in your hand right now, hold it out. This pen has positive potential energy if you reference the floor, but it has negative potential energy if you reference the ceiling, right? So in some sense, this direction of potential energy, or the direction of change in potential energy, is a little bit cumbersome or a little bit hard to understand. Here, we are defining it in such a way that the potential, not potential energy, but the potential decreases as along the direction of field lines, which means the potential is highest next to the positive charge, lowest next to the negative charge. Again, because I define the direction of the field, this is arbitrary. I'm imposing my will on my characterization of nature. Nature does not care. But the reason I'm harping on this is this leads to some really strange, it leads to some pitfalls that you'll need to avoid. So, to figure those out, let's look at this situation. Let me take a collection of positive charges over here, and a collection of negative charges over here. This is going to represent a system we're going to do a lot of work with in the coming days. Let me draw in the field lines. They're going to point from positive to negative, just like this. Okay. Now, let me put in I'll do this in red, you'll be able to see it. Let me put in, nope, I'll do it in green since I've already used red. Let me put in, sorry, my marker's over here, a positive charge. So I'm going to put in a positive charge over here next to my positive charges, and I'm going to hold it still. All right, make sure that's in frame. Good. Now, do you agree, and I know you can't answer me, but do you agree that this charge has potential energy? I hope you're going to say, yeah. How do you know? Well, just intuitively, if you let it go, what's it going to do? It's going to move that way. It's going to accelerate that way. It's going to feel a force, which accelerates it that way. And that is to say, the potential energy develops into kinetic energy. And because of how we've defined this, we're going to say that positive Q is at a high potential. How do I know it's at a high potential? Because what I said a while ago is that the potential is highest next to the positive charges. The field lines point in the direction of decreasing potential. So the potential is decreasing. It's like I'm going downhill, and I'm going to use that analogy a lot when we study electricity. You can think just as this ball rolls downhill because it goes from high potential energy to low potential energy. This charge will move to the right because it's going from high potential to low potential. It's also going from high potential energy to low potential energy, so you can characterize it like that if you want to. But we're talking about potential, so we define it as high potential, low potential over here, right? So the Q is at a high potential, and we say positive Q has high potential energy, right? And hopefully that is obvious. High potential because we define potential to be greatest next to the positive charges. High potential energy because if I let it go, it's going to move, right? So two different reasonings to get these two different things. Okay, fair enough. Let me put in now, and I will do this in red because it's my only other color, a negative charge over here. All right, now, what can we say about this? Well, first thing I can say is that negative Q has a low potential, right? Because I've defined, and I keep saying that because it's important, I've defined next to the negative charges as the lower potential. Field lines point along the direction of decreasing potential. Okay, so negative Q is sitting at a low potential. No big deal. But what happens to negative Q if I let it go? Well, it's going to feel a repulsive force from these negative charges. It will accelerate to the left. So it's a little bit difficult for me to say that it has a low potential energy, because in point of fact, negative Q is going to act in the left direction, just like positive Q is going to act, but in the right direction. If I let it go, zip, it's going to accelerate across this gap. And so I've got a real quandary. I have to say negative Q has a high potential energy. And so you see the confusion, right? The potential we define. So no matter what, this is low potential, this is high potential. I defined that. But potential energy, I don't really get to define that. Nature really kind of prohibits me from doing that. And when, of course, I say a high potential energy, I mean high with reference to over here, right? This thing is sitting at a higher potential energy. As it moves over here, it will come to lower and lower potential energy. So the positive charge sees to the right as downhill. The negative charge sees to the left as downhill, right? The ball that I let go on a hill is going to roll down the hill because it moves from higher potential energy to lower potential energy. Same thing here. This ball will roll downhill. This ball will roll downhill. But I've defined this is low potential, this is high potential. So be careful here. It might just help to memorize this. You say, well, surely there's a way around that. Well, the only other way around that is to completely redefine field lines for negative, if I'm dealing with a negative charge. And we don't want to do that, right? That's actually more trouble than it's worth. So the easiest route is actually to just memorize this or try to understand what's going on. And so I wanted you to see that sort of hidden pitfall there. All right. Now, yeah, that's all for this video. We will do some example problems when we meet for class and for Zoom calls, and I've got some on the playlist, I believe, which I will put up. But for now, no, sorry. One more thing. I knew there was something else. We need to talk about one little special case. All right. So we know units on all this stuff, right? We know that the units of potential is voltage, but I've known for a long time, at least since Physics 1, that the units of potential energy have to be joules. Okay, so let's do this. Let me set up a similar situation here. Positive charge, negative charge, negative charge. And I've got an electric field that looks like this. And let's say that the potential difference across, and that is the correct language, potential difference across these two charges is exactly 1 volt. Okay, no big deal. That's a pretty small voltage. But and this is how we determine the electric potential. I measure between 2 points. Just like what I said, the only thing physically meaningful about potential is how it changes between 2 points. Well, if I measure it across these 2 points, I get 1 volt of potential. Into that potential, I'm going to place I'll do this in green, a single electron. And I'm going to put it over here. Yeah, I'll do that. That's fine. Single electron. So I know that the charge of an electron is minus E, where E is my fundamental charge, right? And the number, I just happen to know what that is, minus 1.602 times 10 to the negative 19th coulombs. Okay, fair enough. All right, and suppose I say, all right, how much potential energy does this charge have when I put it there? Another way of saying it, if I let it go and it goes across the gap, if it moves across the 1 volt of potential, how much kinetic energy has it gained, right? All of this potential energy is going to turn into kinetic energy. It's a conservation of energy problem, just like you did with gravity. But I can ask the question either way. But let me just say, how much potential energy does this have? Okay, Fair enough. I know an equation for that now. I know that potential energy is equal to QV. In this case, this is my charge. My voltage is 1 volt. I'm going to get, let me leave off the negative sign. I'm just going to deal with the magnitude. Let's suppose I say, what's the magnitude of the potential energy? All right, I'm going to get 1.602 times 10 to the negative 19th coulombs times 1 volt. Well, I can do that math in my head. Anything times 1 is just that thing. This is equal to 1.602 times 10 to the negative 19th. And I know that my units have to be joules. As it turns out, when you take a coulomb and multiply it by a volt, you do indeed get a joule. 1.602 times 10 to the negative 19th joules. That is an impossibly obnoxious number to write down all the time, right? 1.602, and then this 10 to the negative 19th. If I've got to drag that around, if I'm doing problems involving energies of this level, this is really obnoxious to have to drag that around. So what do we do when we're physicists and something is obnoxious? We redefine it in terms of something easy. So let me redefine this number. This number, 1.602 times 10 to the negative 19th joules, I'm going to define as a new unit. That is 1 electron volt, or EV for short. Now, notice this charge is E and I'm multiplying it by 1 volt. That's the implication of this, but be careful, this is actually a unit. EV is 1 electron volt. If you've taken a chemistry class, I imagine you've seen electron volts before, usually with MeV, if you know the ionization energy of the hydrogen atom, 13.6 EV, right? So if you haven't taken chemistry, that's okay, you will and you'll see it. But for our purposes, this is a handy unit of energy when I'm dealing with really tiny bits of energy. Basically, if I'm dealing with atomic or subatomic measures of energy, and I've got all these really small quantities going around, it's easier to write 1 EV than it is to write all this stuff. So I wanted to introduce you to that. We're not going to see that again for a while, but we will see it later in the semester. So I wanted you to see it now.